All right, in this video, we are going to talk about Chapter 7, Section 1, about some algorithms for finding spanning trees. So, an algorithm is just a finite sequence of well defined instructions used to solve a class of problems or to perform a computation. So, basically, a set of steps. They have to be well defined, not ambiguous, and they have to terminate in a finite amount of time, so a finite sequence of these instructions. And so you'll use these to solve some class of problems. So in this case, we are looking for spanning trees. That's what we're going to be doing, or to perform some other computation. A lot of times these, after you find an algorithm, right, you can write a computer program to carry out those computations. We're not going to be doing that, although you certainly could with the ones that we were talking about. Another area of algorithms that is important, but we will not really take a look at, is the efficiency of algorithms. Sometimes you'll have competing algorithms for solving the same class of problems, and then the thing that you would want to do is to say, okay, which class of algorithms is more efficient for solving this particular problem, and take a look at that. So while that is important, we won't be doing that in this video. All right, so our problem is finding spanning trees, and so given a connected graph, find a spanning tree of the graph. All right, and the algorithms that we are going to take a look at in this section will basically grow these trees by adding vertices and edges to an existing tree one at a time. So we'll start off with a small tree, a vertex, or maybe just a single edge between two vertices, and then we'll start adding vertices and edges to that tree in such a way that each time when we add a new edge or vertex in there, then the resulting graph will also be a tree. Okay. All right. So the very first one that we're going to look at is called the BreadthFirst Search algorithm. There's ways to do this, and so we're just going to basically follow the method outlined in the book here. Okay. So, given a connected graph G, this algorithm will produce a spanning tree T of G. All right, and so the algorithm works like so. So what you would do is select any edge of G and label the endpoints of the edge E that you select by V1 and V2. Okay, and then add the edge to the tree T. So prior to starting the algorithm, then the tree T is empty. It doesn't have any vertices or edges in there. A lot of times you'll see this algorithm that you'll be given a particular vertex to start at. But in our book, the version of this, it just starts off by adding the edge E in there and then labeling the vertices 1 and 2 that are the endpoints of this edge E that you added in there. Okay? So then we're going to introduce two variables, I and j. So I will keep track of the current vertex that we're at, that we're looking at. All right. So the very first vertex, V1, is going to be considered the vertex that we're starting at. And so I will start off as 1. In this case, when we add the vertex in there. So think of the variable I as representing the current vertex that we're at. And then j will represent the next label, the label that we'll give to the next vertex that's added to the tree, right? So the tree starts off with this edge E, right? And we label the endpoints of that edge V1 and V2. So 3 would be the next label for a vertex that we add. Okay. All right. So I is the current vertex. J is the next label. All right. So then step 2 is to check whether the neighbors of v sub I in G are all in T. All right, in this case, so in the very first case, it would be I equals 1. Okay. And so you would check the neighbors of V1 and see if they are all in T. So you would look at vertex 1, look in the graph, and basically there's going to be two cases, right? There might be some neighbor of V sub I that's in the graph but not yet in the tree. Okay, so in that case, what you want to do is label that vertex V sub j. So you will use the next label, okay? And then you would put that edge into the tree. All right, so you would add the edge, the vertex V sub j, and the edge going from V sub I to V sub j into the tree. All right, and so if j is equal to the number of vertices, then you would stop, because that would mean that every single vertex has been used up and the output is going to be a spanning tree. Will need to verify that that is the case, right? That the result of this process ends up with a spanning tree. Okay. So if if j is not equal to the number of vertices, right, you would increase j by 1. This probably looks a little strange if you haven't encountered something like this in computer science, but basically this just means you are going to increase the value of j by 1. All right, so that means you'll have used up whatever the previous next label was, and so then you'll have to update that next label. You'll have to update the variable j, and then return back to the step 2. Okay, so check the neighbors. If there's a neighbor that's not a neighbor of the current vertex that's not in the tree, you're going to give it whatever the next label is. You're going to add that vertex and the edge in there, and then increase the value of j. If you're not haven't used up all the vertices, all the vertices, you're going to increase the next label. Then if on the other case, when you check the neighbors of the current vertex v sub I, if they are all in T, if they are already all in the spanning tree, then what you're going to do is increase the current vertex by 1, right? So you're going to increase the variable I by 1 and move to vertex number 2. And then go back to step 2 and start checking the neighbors of vertex 2. Okay? All right, so the best way to deal with that is to go through an example. All right, so we are going to start working through an example of the BreadthFirst Search algorithm. And so what we need to do is to pick an edge to throw in there and label the vertices 1 and 2. So I'm going to label this one 1 and this one 2. I know it says V1 and V2, but we can just write the numbers here in this case. All right, and so this is the edge that is in the algorithm, this one right here. All right, so this is what our tree looks like so. Okay, and then we need to keep track of the variables. So remember, this is like the current vertex, and maybe I'll write that. And we set that to 1, and then the next label is j, and we set that to 3. Right, we've already used 1 and 2. Okay, all right, and so then the next thing that we would do is to look at the current vertex, right, which is vertex 1. And we would look at all of the neighbors of it, and we would ask ourselves, hey, does vertex 1 have any neighbors that are not in the tree? And it does, right? It has this neighbor right here. So if we look at the algorithm, right, we're checking to see whether the neighbors of V1 are all in T. And in this case, there is a neighbor of V1 that is not in T. So what do? you give it the next label, right? So what we would do is mark this one as 3. All right, so that's what you would do. And then add the edge into the tree, okay? The edge from V1 to V3 in this case. Okay, so we would add that in there. So I'm going to color it red to show that it's inside the tree. All right, and then it says if j is equal to the number of vertices of the graph, then stop. Well, it's not, right? There's a lot more than 3 vertices in this graph. And it says otherwise, if it's not, then set increase j by 1. Okay, so we're going to increase j to 4. So the next label now is going to be 4. Okay. All right, and then go back to step 2. Right. Remember, step 2 is this: check whether the neighbors of v sub I and g are all t. In this case, we're talking about v1 since I is 1. Right. That's the current vertex. And we'll see, right, that all of the neighbors of vertex 1 are already in the spanning tree. There's no other neighbors. So that sort of drops us down to this case right here. If all of the neighbors of v sub 1 are in G, increase I by 1 and return to step 2. All right, so that's what we're going to do. So now the value of I is 2. All right, so now 2 is the current vertex, and we would do exactly the same thing that we did with vertex 1. So now we're going to start looking at the neighbors of 2. Are there any neighbors of 2 that are not in the tree? There certainly are, right? So this one right here. All right, and so we would add that label, that edge, and that vertex into the tree. And then we would increase j by 1. All right, and then we'd ask ourselves, okay, again, we're on label 2, going back to step 2. Are there any neighbors of it that are not in the tree? And the answer is yes, right? So this one right here is not in there. So we're going to call that one 5, and then add that vertex and the edge joining 2 and 5 into the thing here. Okay. So one thing I want you to notice, right, is at each stage, right, we had a tree. We had a tree here, right, when we had one edge, and then we added 3 in, right, we had a tree, then we added 4 in, we had a tree, then we added 5 in and added a tree, right? At each stage, it is a tree. It's a tree, right, because number one, we don't have any cycles. Each time we add an edge, or add a vertex and an edge in there, that new vertex is only connected to one of the tree elements, right? And so by adding that new edge in there, we don't put any cycles. To make a cycle, it would have to have 2 edges coming from it, right, for that new vertex to create a cycle, and we don't do that. And each time it's connected as well, right? Each time, like we just added this vertex 5 right here, we can see that it was a tree before we added, right? So there was a path between any 2 vertices. So when we add this new vertex and this edge in here, there's a path between 5 and any of these other vertices in here. We would just take and go to the vertex of the tree that it's connected to, and then take the path from there. So it remains connected in each stage. Okay, so each stage we get a tree. All right, so we added 5 in, and then now we need to increase. So the next label is going to be 6. All right, and checking 2, we see if its neighbors in the graph are in the tree. So 3 is, right, 4 is, and 5 is. And so all of the neighbors of vertex 2 are in the tree. So what we would do is increase the value of 3 here, okay? Value of I, the current vertex, to 3. So we would go on over to 3, right, and check, are its neighbors already in the tree? Its neighbors in the graph? Well, 2 already is, 1 is, right? 5 already is, but this one is not, right? And so what we would do is give that one the label 6, and then add it into the tree. Okay, so we've done that. Then we need to increase the next label to 7. All right, and now looking at 3, our current vertex, right, all of its neighbors in the graph G have been added in, so now it's time to increase that to 4. All right, and then we would go to 4, right, and we can see, okay, this neighbor is not in the graph, so I'm going to add that in there. Now you may say, hey, well, there are several neighbors of 4 that, or at least 2 neighbors of 4 that that aren't in the tree. How do I know which one to add? And you can, it doesn't really matter how you do that. Sometimes if these things have labels already, the vertices have labels already, then you can break the tie by, if they're numbers, you can take the smaller number, or if they're letters, you can take the lexicographical order, right, to break the tie between the vertices. All right, so now we would increase the next label to 8. All right, then going back and looking at 4 again, we can see that this neighbor doesn't have, is not in the tree. So we would go ahead and add that in there, increase this to 9. Okay, and so then we would look, and all of the neighbors of 4 in the graph G are already in the tree, right? And so therefore we would increase the current vertex to 5. So then we would go over to 5, right? And we're looking again for neighbors of 5, that is vertices that are adjacent to 5, that are not in the graph. And there is one right here, so that would get 9. And we would add that to the tree. Okay, and then increase the value of J. Go back, and now all of the neighbors of 5 are in the graph, in the tree rather. And so then we would increase I, the current vertex, to 6, right? And then start checking the neighbors of 6, and we can see right here 10, right, is not in the tree, so we add it in there. All right, so we've added it 10 in there, and that is the number of vertices, right? So that hits this line right here. The current label now is equal to the number of vertices, and so we would stop. And that tree that we have in the picture is the spanning tree. Okay. All right, so that is an algorithm for determining a spanning tree. You might say, well, because we've done some examples of finding spanning trees by hand, and at that point, for the graphs that we looked at, they were, fairly small, and so it wasn't very hard to do that. But if you have a huge graph, right, that you want to go through, and you want to, visit every vertex once in an efficient way possible, if it's connected, then this algorithm is an example of an algorithm that gives you a nice, orderly way of doing that. Okay, so that's an example of how the BreadthFirst search works. And with any algorithm, it's also important that you verify or prove, that the outcome is what you want. And we aren't going to do that with every single one of the algorithms that we look at, because some are pretty difficult. But so this one I already kind of mentioned why this works, right? Number one, right, at every stage when we're growing this tree T, the tree contains no cycle, right? It starts off with an edge, just one edge, so that contains no cycle, because with a graph, you have to have at least 3 edges, right, to have a cycle. And then every time we add a vertex, that new vertex that we add is incident to exactly one other vertex in T. So if there was no cycle before, then when you add that vertex and it's only incident with one edge in the previous version, the previous tree, that can't introduce a cycle, okay? Because if there was no cycle before, adding one edge, right, from a vertex that wasn't in the tree to one that's in the tree, it's exactly one, that won't form a cycle. You would have to have another edge from the new vertex that you added in there to back to the tree to make some kind of cycle, and that just hasn't happened. So in every single stage, that T has no cycle. And likewise, T is connected from what we mentioned, because at any stage T, the tree, right, it is connected because it's a tree, and then when we add the new vertex in, right, there's an edge going from that new vertex to one of the vertices that's in the tree. So that means that with that new vertex, there's a path, right, from that new vertex to any of the other vertices that are in the tree. And if the 2 vertices are in the previous version of the tree, then there's a path in the previous version. So every time we add that edge in there, the way this algorithm works, we get it connected. So in every stage, right, it's a connected graph with no cycles, and so therefore it is a tree. And then finally, T is a spanning tree, right? This goes back to the fact that G is connected, right? The original graph that we start with is connected. And so what that means is that there is a path in G between any vertex of G and some vertex in the tree. So, and then what happens is that one by one, those vertices in the path are going to get added to the tree, right? And then eventually that next to last vertex between whatever the last vertex is going to get added, and when we're looking through all those neighbors, eventually that last vertex will get added in there. Okay, so there's no way we could have a vertex left out in here since G is connected. All right, so that means that we get a spanning tree every single time with this BreadthFirst Search algorithm. All right, so that's it for this video. In the next video, we're going to talk about a different algorithm and sort of a different type of problem related to spanning trees.